Chapter 9, Section 3. In Section 9.1, we looked at a function that had two variables. We found that if we set one variable to be constant, we could interpret the cross-sectional data for that function. In this section, we'll take a closer look at the rate of change of one variable function using what's called a partial derivative. So when we had functions of one variable, we had one derivative. When we have functions of two variables, we have what's called two partial derivatives. Now, if we have a single variable function, we can find the rate of change with respect to the variables x or y by taking the partial derivative. For instance, if y is fixed, or a constant, at 5, we can change a two-variable function, f equals f of x equals 175x plus 325y, to a single variable function by plugging in that y value. If we plug in that value of 5 for y, our function becomes 175x plus 1625. This function here is a single variable function. So now we can take the derivative of this function with respect to x because we know how to take the derivative of a single variable function. So here, the derivative with respect to x, when y equals 5, is just 175, because the derivative of 175x is 175, and 1625 is now a constant, so that goes to 0. Now let's look at a little bit of notation. Here, we have this sort of backwards 6, and this represents the fact that we're taking a partial derivative. So this says the partial derivative of f, our general function, with respect to x. So that means we're taking the derivative of the x variable. That means the y variable is a constant. So when y is constant at 5, f increases at a rate of 175 with respect to x. We can perform the same steps to find the rate with respect to y, but this time let's set x equal to 5. So now again, if we plug in a 5 for x, we get 175 times 5 plus 325 times y. That turns our function into 875 plus 325y. Notice now again we have a single variable function, so we can take the derivative. So the derivative of 875 is 0 because it's a constant, and the derivative of 325y is just 325. So we say the partial derivative of f, the general function, with respect to y is 325. This means that when x is a constant at 5, f increases at a rate of 325 with respect to y. Now, we'll do a lot more of these partial derivative calculations in the next section, but this is a general idea of what's going to be going on when we start to look at how these function. So, where do these come from? So the partial derivatives are calculated the same way regular derivatives are, but with two variables. So here, let's look at some notation. If you're going to take the partial derivative of a function with respect to x, so this little subscript tells you which variable you're taking the partial of, at ab, so we're plugging in some point, that's the rate of change of f with y fixed at b, and at the point AB, and that's calculated through a limit. There's more detail of how these limits are calculated at the end of the book section if you're interested. Similarly with y, the partial derivative with respect to y is going to have this subscript of y to tell you which variable we're taking the derivative of at a specific point, AB, which equals the rate of change of f with x fixed at a at the point AB. So, if we treat a and b as variables, a is x, b is y, then we have the partial derivatives of the functions f sub x, xy, and f sub y, xy. If you take the partial derivative of the function without plugging a number in, you're generally going to get a function or a constant back. However, if you take the partial derivative and then plug in numbers, you're going to get a number back. Like I said before, we're going to do a lot more of the algebraic calculations in the next section. Okay, alternate forms of notation, just so we're all on the same page. So suppose that z is a function of x and y. One way that we can say the partial derivative with respect to x is f sub x at xy, which is the same thing as this backward 6, so partial of z with respect to x. These mean the same thing. Over here, the partial derivative of f with respect to y, again that subscript tells you the variable you're taking the derivative of, at xy, that's the same thing as saying the partial of z with respect to y. Now, just like before when we did integration, we had some notation for when we were plugging numbers in. So that's what the second row stands for. So if you take the partial derivative of x at ab, then that's the partial derivative of z with respect to x. And then we draw this line, and we write AB to tell us what values of x and y we're going to be plugging in. Similarly, f sub y at AB is the same as the partial of z with respect to y at AB. The symbol helps us to know that a partial derivative is being taken as opposed to a regular derivative. Okay, so when we start our analysis of actually calculating these partial derivatives, what we're going to focus on in this section is tables and just a little bit on contour diagrams. Like I said before, in the next section you'll learn how to calculate them algebraically. So let's say that a lab experiment was conducted on rats to determine the effects of mercury exposure during a prolonged period of time. The percent, capital P, of rats surviving the experiment with concentration C in parts per million after T months are represented by P is a function of T, time in months, and C, concentration they were exposed to. And that's given in the following table. So again, the way we're going to read this table is if we pick some value in the middle, say here. This says 16 months, and the rat was exposed to 2 parts per million, and 99% survived. Again, these middle values are the percents of surviving rats. Time is across the top, concentration is down the side. Okay, so how do we go about estimating partial derivatives from tables? It's very similar to how we estimated derivatives on tables when we were doing regular derivatives before we had two variables. So if we want to estimate the partial derivative with respect to c at 20, 2, and the partial derivative with respect to t at 20, 2, for this function in the table we're given, how do we do that? So let's start with the partial derivative with respect to c at 20, 2. Now again, when you take the partial derivative with respect to c, that means that t is going to be fixed. So here, since t is 20, we're focusing on this column. Okay? So if we want to estimate the partial derivative at 2, what we want to do is we want to look at how much the function p, the whole entire function, is changing with respect to how much the concentration is changing. So what we want to do is we want to use a right-hand estimation. So what that means is we're going to be looking at the value 20, 2, but also the value 20, 6, because again we've fixed this column, and so that's the next closest value to use. So what we want to do is look at the value of f of 20, 6 minus the value of f of 20, 2. So we want to look at the difference in the next step. So that's going to give us 90 minus 97 divided by the change in concentration. Well, that was 6 minus 2. So 90 minus 97 divided by 6 minus 2 gives us negative 1.75% per ppm, because that's the units on our concentration. Now if we want to estimate the partial derivative with respect to t at 20, 2, now since our derivative is with respect to t, we're going to be fixing our concentration. Well, concentration is the second number, which is 2, which means we're focusing on the 2 row. Okay? So similarly, we want to find out what's going on at 20, so we use the next value up to help us estimate. So here the next value up is 24. So we're going to be using this 97 and this 92 because this row is fixed here. So the change in percentage, we're going to do f of 24, 2 minus f of 20, 2. So that's going to give us 97, or 92 minus 97 divided by, now the change in time is 24 minus 20. So 92 minus 97 divided by 24 minus 20 will give us approximately negative 1.25% per month, because t was in months, and that's what's on the bottom here. So again, you need to sort of look at what's going to be fixed, and what's going to be fixed is the number that you're not taking the respect to. So again, here with the t, this partial derivative was with respect to time, so we fix the concentration at 2, then we go to 20, we use the next step. Okay, so we fix a row here. Now that we have these estimates for the derivative, what can we do with them? Well, when we had derivatives back in chapters 2 and 3 of Calculus 1, we would often use them to get other estimates for values on the table that are not filled in, using something called local linear approximation. We can use partial derivatives similarly to get estimates for values that are not on the table. So let's see how that works. Suppose we want to estimate something that's not on the table. So here, let's say we want to estimate the function value at 20 months and 4 parts per million for our concentration of mercury. Notice here that we do have a column for 20 months, so that's helpful. However, we don't have a value of 4 for the concentration. So since we don't have the value of 4 for concentration, we want to use the partial derivative with respect to concentration to get an estimated value to represent that 4. So in the last slide, we calculated that the partial derivative with respect to c at 20, 2 was negative 1.75 per parts per million. So what we can do, like I said, which is similar to local linear approximation, is we can take the value at 20, 2, which is 97%, and then add to that the partial derivative, the rate of change of c, times how many spaces we've moved from c. So the new concentration we want minus the concentration we use, so 2 units. Plugging in those values, we have 97% plus our partial derivative with respect to c at 20 was negative 1.75, and now we're moving 2 units away from 2. So again, our estimate was for the value concentration of 2, but now we're estimating at 4, so we've moved 2 units away. So 97 plus negative 1.75 times 2 gives us an approximation of 93.5% of rats survived at this value of 20, 4. Now, what if we want to estimate the value of the function at 23, 2? So again, we look at what we have on the table. We look for 23. We don't have that value in months. We look at the concentration value of 2. We do have a concentration value of 2, so we'll only need to estimate something in terms of months. So that means in this particular case, we want to use the partial derivative with respect to t. Now to get 23, we're going to want to use 20 because that's going to be the one right before it. So here we found our partial derivative is negative 1.25% per month. And now, since c is fixed, we're increasing t from 20 to 23. So we take the value at 20, 2, which was 97%, because again, 2 is our concentration. And then we use the partial derivative to represent the rate at which we're changing times the amount that we moved. So here, since we went from 20 to 23, that's the number of units that we've moved away. So here, when we plug in these values, we get 97% as our value of f of 20, 2. Our partial derivative at 22 was our negative 1.25, so that's how much our function is changing with respect to t, and we've moved 3 units. So 97 plus negative 1.25 times 3 is going to give us an approximation of 93.25% of rats survived at the value 23, 2. So you can see how we can use these partial derivatives, just like local linear approximation, to see how much we've moved. Now for both the cases we've just looked at, one of the values, either concentration or time, was one given in the table. Sometimes we want to estimate a value where neither of them can be fixed. So let's look at that. So say we want to estimate the function at 22, 3. So again, 22 is not on the table, 3 is not on the table. So what we want to do is we want to see which value is closest to 22 without going over, so that would be 20, and which value is closest to 3 without going over, which is 2. So we want to use the point f of 22, and then from there we want to change with respect to our rates. Well, these are the rates we calculated first. So the derivative with respect to t at that point was negative 1.25. The derivative with respect to c was negative 1.75. So we take the functional value plus, then we multiply the partial derivative with respect to t times the number of units we're moving away. So here we started at 20 and moved to 22. Again, the new number you want minus the number you use, so 2 units, plus, and then the partial derivative with respect to c, so the rate of change of concentration, and then here the new number we want is 3, minus the number we used is 2. So we get to use both partial derivatives in this case. So that gives us 97, which is f of 20, 2, plus negative 1.25, that was our partial with respect to t, times 2, the number of units we're moving away, plus negative 1.75, that's our rate of change of concentration, times 1, the number of units we're moving away. Crunch all these numbers in your calculator, and we get an approximation of 92.75% of rats survived for 22 months at an exposure of 3 parts per million. So we can estimate any value on the table by using our partial derivatives. Now that we've looked at tables, we also want to very briefly touch on how we can look at contour diagrams, which we learned about in the last section, to just estimate what's on with partial derivatives. So let's look at a quick graph and see how that's related. When we estimate partial derivatives using contour diagrams, the first thing that we want to really be able to do is determine if our partial derivative is positive, negative, or 0. So the sign is going to be really important. When we only had single variable calculus, it was easy because we could draw on a tangent line and see if it was positive or negative. We can't do that here. We can't simply draw something in to figure it out. So what we need to do is look at if the function is increasing or decreasing at the point at which we're trying to take the partial derivative. So here we have a graph of h of t, x. T is in minutes, x is in feet. So what we want to do here is we want to look at the partial derivative with respect to t at 15, and determine is the partial derivative positive or negative, and the same thing with the partial derivative with respect to x. So let's start with the partial derivative with respect to t. So here, if we go to the point 15, which is right about here, and we want to know, is this partial derivative positive or negative? We want to look at whether the function is increasing or decreasing with respect to t first. Okay, so we want to know, is this function increasing or decreasing with respect to t? So what we do is we have a fixed value, and now we're going to move up t to see if it's an increasing or decreasing function. So we're on the 75 contour. As we move up, we hit the 80 contour, and then the 85 contour. So our function h is an increasing function of t. So that tells us that the partial derivative will be positive. Okay, because if we're increasing, it's positive. Now, if we take the partial with respect to x, again we start at 15, 15, but now we increase x to see what the values are doing. So we're on the 75 line. As we move right, you're going to see eventually we're going to hit the 70 line, and if we kept going, eventually we'd hit the 65 line. So 75 towards 70, that's a decreasing function of x. If it's decreasing, that means the partial derivative is negative. So you want to get used to looking at whether or not contour diagrams are increasing or decreasing within a variable, because that will also tell you the sign of the partial derivative.